Let's solve the energy crisis one potato at a time. I teach a lot of physics and electrochemistry to my students, and one of the things, even at a university level, that I try to get them to do is build a potato battery. It is really important to instinctually understand and intuitively understand a lot of aspects about batteries that, even though we can study on paper, takes a while to build an instinct around it. A potato battery can teach you about so many concepts. First of all, about voltages in series and parallel, about current in series and parallel, about current density and internal resistance. That's a lot of things to cover when you're just building a potato battery. The idea behind the potato battery stems back to the first voltaic pile ever created, the first battery created by Alessandro Volta, where he piled copper and aluminium plates, or was it zinc, with soaked salty water cardboards in between. Because there is a potential difference between the zinc and the copper, when you close the circuit, electrons from one surface of the plate wish to travel to the other, and it travels through the soaked, salty cardboard as the medium, as the electrolyte. Every metal has a unique electrochemical potential. So between copper and zinc, we have about a potential difference of 1.06 volts. These are two very good plates to use in our setup with the potato. So one of the plates that we're going to be using, as you can see, is zinc, and the other is copper. If you want to get access to these metals at home, usually a copper coin can do the trick, and a zinc coated nail. So let's build our battery. Here I've hammered in the zinc and the copper plates, and so now there's a potential difference between them, and it's going to use the potato's juices, quite literally, as the electrolyte to pass current through. An LED requires about 1.6 to 2 volts to light up, specifically the red LED. In my past experience, it takes about 3 potatoes to actually get the LED to light up, but in this case, I was very lucky and it only required 2. You add the potatoes in series to increase the voltage. We don't need to increase the current, because first of all, there is sufficient current density, and generally speaking, LEDs require very little current. If I needed to increase the current, I would put them in parallel. What do we mean by current density? Well, take the zinc plate, for example. If all of this was immersed in the potato, every single surface of this metal can contribute to the current. However, if I only immersed half of this zinc plate in the potato, only about half of the current, possibly at any given moment in time, could flow. This is what we mean by current density. It's current per unit area. My rabbit is being weird. I think she's judging me. So when you put potatoes one after the other in series, you're building up the voltage. But the current is always going to be limited by your worst immersed plate. What do I mean by that? Have you ever heard of the figure of speech that your team is defined by your worst player? Well, that's exactly what happens to potatoes when they're put into series. Whatever is the smallest surface area plate that is immersed in the potato will be the current density that will be maximally achieved. It doesn't matter if you increase all the other ones. If one of them is limiting your current, that's the cutoff point. You can play around with this by putting your multimeter in series and slightly pulling out or pushing in one of your less immersed plates. This should affect the current measurement. The electric potential for copper is 0.34 volts when compared to hydrogen. And for zinc, it is minus 0.76. So that gives us about a 1.1 volt, which means that potentially we have 1.1 volts in each potato. As you can see from these measurements though, that's not true. Where is the remaining voltage coming from? Well, there's actually a lot of complicated processes, but chances are it's got to do with the internal resistance of the potato itself. If you study any bit of electronics, sometimes you are forced to take into consideration the internal resistance of your battery or voltage supply system. It's usually added as a resistor in series, and so you measure its drop by I times R. This is the exact same case in our system. Now, there is resistance between the interface of the metals with the contacts of the clips and obviously the wires, but most of it, chances are coming from the potato itself. Why? You might ask, well, why is there an electric potential difference between zinc and copper? And in fact, pretty much any plates. You can test this with aluminium, iron, different types of metals. Generally speaking, it's got to do with the work function of the electrons. Some metals want to give their electrons out more than others. It gets a little bit more complicated in more advanced physics, but that is a very nice introductory level to the concept. And this is why I think the potato battery is amazing. We covered the concepts of internal resistance, current in series and parallel, voltage in series and parallel, electrochemical potentials, discussed current density, and in the process got to build something and mess around with real live objects. I think this is a very powerful tool to teach students about these concepts. I better go. That bunny looks like she's about to murder me.